Where do I start? Not only have I pondered that question for this assignment, but scientists and their theories, such as the Big Bang, attempt to answer the fundamental questions, such as where did it all start? One of the first questions about space we sought to answer was only just 200 years ago. It was if the universe is comprised only of the Milky Way galaxy, or was there more? In 1929, Hubble compared the distances of galaxies to their visual redshift and found a linear relationship. Not only did this answer their question regarding if the universe was a Milky Way, but this also was huge evidence supporting and developing the Big Bang theory. Redshift occurs due to the Doppler effect, which says that the wavelength of light changes depending on if the wave source is moving towards or away from the detector. Scientists believe that the universe is expanding due to evidence of redshifted light coming from galaxies that are far away from Earth. Before the Big Bang happened, it was called the singularity because we had no idea how it works and also defies physics. But during the singularity, the entire universe is compressed very, very small and very, very hot. Then the Big Bang happens, and that's a terrible name because it's more of a stretching than an explosion. But during this hot and short moment, matter, energy, and space was created. Once things cooled off, there were recognizable elements such as hydrogen and helium. So now what? You have an infinite amount of matter, energy, and space. Where does it go from there? Well, beginning as a cloud of dust and gas called a solar nebula, it then contracts under its own gravity. This is the condensation theory. And this also explains how it starts out as a 3D form, but ends up as a flat 2D disk. Not only is it flat, but it also begins to rotate. And as it rotates, large and small clusters begin to form. The large clusters orbit the center of the solar system, and this is the beginning of stars and planets as we know them. They then ultimately form solar systems, such as our own. And for a while, we believed in the geocentric model, where Earth is at the center. But as we now know, the Sun, a sphere 100 times greater than the size of Earth, and a scorching hot ball of gas, is in fact the center of the solar system. Our solar system consists of 8 planets. There are terrestrial, like Earth, with characteristics such as small, rocky metallic, dense, and solid surface, and Jovian planets like Jupiter that are typically larger, have many moons, have planetary rings, and are not dense. There are more than 200 moons in our solar system, some even bigger than planets. Moons orbiting a planet can and will change the orbital and rotational trajectory. This is backed by Newton's laws. For every action there is an equal and opposite reaction. As the Earth pulls on the Moon with an equivalent amount of force that the Moon pulls on the Earth. And we can see that in work here on Earth. Just take a look at the ocean. High tides and low tides are caused by the Moon. The Moon's gravitational pull generates something called the tidal force. The tidal force causes Earth and its water to bulge out of the side closest to and the side farthest from the Moon. Let's take a look at some more waves, like an electromagnetic wave. Transferring heat by radiation is how the Sun can pass off energy and have it reach all the way to Earth to heat our surface. Light is also a great example of transverse and can travel well through space, although the light we can see is only a small bit on the spectrum. There are also UV, X-ray, gamma, infrared, microwaves, radio waves, all differentiating in frequency, which is how many oscillations occur over time, and or wavelength, measuring the distance between points on 2 oscillations, and amplitude, or the displacement of an oscillation from the point of equilibrium. Looking on a submolecular level, we find modern physics. Modern physics is divided into atomic physics, which is small, and nuclear physics, which is even smaller. Atoms are the building blocks of modern physics, and the building blocks of atoms are protons, which are positively charged ions, neutrons, which are neutral, and electrons, which are negatively charged. Elements are the simplest forms of atoms, as they cannot be broken down to form new things. They are also atoms having an identical atomic structure to one another. However, there are isotopes which have the same number of protons but a different number of neutrons. Be careful, if the atomic number is greater than 83, then it is radioactive. Rutherford nuclear model, discovered by using particle scattering, that 99.97% of atoms' mass is concentrated in the nucleus. The dinky 0.03% is very important, of course. Electrons. They orbit the nucleus, and the outermost electrons in the atom is known as the valence shell. The octet rule applies to them, and the elements tend to bond in an attempt to gain 8 electrons in the valence shell, making it a noble gas configuration. Chemical reactions are changes in the chemical composition, state, or rearrangement of original bonds. Atoms can bond to each other through ionic, which is a transfer of electrons, or covalent bonding, which is sharing of electrons. There are also intermolecular forces, which aren't bonds, but they are more of attractions. And this includes dipole-dipole, hydrogen bonds, and Strong's force. And through these bonds and intermolecular forces, everything on Earth is created